In math, it's important to understand what category a number may be classified into. So how did you do with what might be some familiar categories or perhaps might be new? Thinking about the number 2, is it a natural number? Is it a whole number? Is it an integer? Is it a rational number? Well, let's do one at a time. The natural numbers are the numbers that you count with, starting with 1, 2, well, I guess it would be a natural number. Of course, 3, 4, 5, and on up. Those are typically the numbers we think of when we make a number line, but officially they're like the counting numbers, the natural numbers. Now, is 2 a whole number? It seems pretty whole, it seems pretty full. In fact, it also is a whole number because whole numbers are actually all the natural numbers, but also the number 0. So the number 2 is also a whole number. How about an integer? That sounds like a familiar word. Well, the integers are the whole numbers plus their opposites. And essentially, we can also have the negative version. But the number 2 would still fit into that category. It's still an integer. And a rational number, maybe you've heard of that word, but basically a rational number can be written as a fraction. Can we write the number 2 as a fraction? Well, sure, we could write it as 10 over 5. Maybe we could write it as 8 over 4. Or we could even just write it as 2 over 1. It would be a rational number. So you would be correct if you said that the number 2 fits into all of these categories. You would also be correct if you had chosen at least one of them. Let's dig a little deeper using our sheet as we talk about topic 4, numbers and sets, and even classifying numbers according to those sets. So look at the diagram that I've given you on the rational numbers. Do you see how in the innermost part of this diagram we have natural numbers? So not every number is a natural number, but there are some numbers that are natural, and as we said, they're the numbers that you count with, like 1, 2, 3, and of course that list can go on. So the natural numbers, they basically are those positive numbers that we count with, starting with 1. Now, whole numbers would actually also be the natural numbers, but would also include the number 0. Now, I'm not going to relist 1, 2, 3 because they are also in that set. But the whole numbers include the number 0. And then 1, 2, 3, and so forth. Now remember, the integers are all of these numbers plus their opposites. So if I was going to list their opposites, I would also be able to add negative of 1, negative of 2, negative 3. And so all the numbers so far that are written in this diagram are integers. The negatives, the positives, and also the number 0. Answer this with a neighbor. Is every natural number an integer? Is every natural number an integer? Now you should be saying yes, but what about the converse to that statement? Is every integer a natural number? Is every integer a natural number? Well, the integers that I've listed here already refute that because -1, -2, -3 are not natural numbers. They are negative. And remember, the natural numbers have to just be those positive numbers. Well, continuing, rational numbers. Every number that's listed so far is a rational number, but there can be more because rational numbers are those types of numbers that can be written as fractions. And their decimal pattern has, well, their decimals have a pattern. We say that there is a pattern to the type of decimal. For example, 2/3 certainly is a fraction, and when we think of that decimal, there's a pattern to it. It's simply 0.6 repeating forever. How about a number like, well, what do you think here? How about 15/7? 15/7. That's also a rational number. It clearly can be written as a fraction. And when you think about the decimal for 15/7, it is awfully sloppy if you put that in your calculator, but there's also a pattern to it, and that's because this fraction contains an integer in the numerator and denominator. As long as the numerator and denominator can be written as integers, then it's still going to be classified as a rational number. But there are some types of numbers who have a decimal that has no pattern to it. It doesn't repeat. And, we could argue that it's awfully sloppy. And numbers like that are shown up in this list would be maybe like the number pi. Maybe you know that the number pi starts as 3.14, but the decimal just goes on and on with no pattern after that. Square root of 2. It looks kind of innocent. It contains an integer, but when you talk about the square root of 2, it's not an even value. If you put that in a calculator, the square root of 2 is approximately 1.41, but again, as you look at that decimal, there's no pattern to it. It goes on forever. It is an irrational number. There's other numbers out there that we'll study this year, like the number e. The number e is actually equal to about 2.72, but it too has a decimal value that just goes on and on with no pattern in mind. So irrational numbers are kind of strange. They are numbers, but they don't fit into any of the classifications that we saw on the left-hand side, mainly because they have a decimal pattern, that has no pattern. I should say that their decimal value has no pattern. Why don't you see if you can classify some of the numbers that we have in practice 1. So even if we have the opposite of pi or negative pi, that is still going to be an irrational number. Three over 2. That is a fraction that's made up of 2 integers. It also has a decimal pattern that has a decimal that has a pattern. It's simply 1.5. We would call that a rational number. How about negative 6? Negative 6 can only be classified as an integer, as the integers contain the opposite or those negative values. 5.31, 2. It looks like it's a decimal. It has a pattern that actually that basically terminates, and because of that, we can say that it's a rational number. By the way, if I was going to write that as a fraction, I could sort of take the easy way out and just write that as 5,312 over, well, how many zeros am I going to need? How many zeros are we going to need? We just need 3 zeros to be able to move the decimal 3 places. So 5,312 divided by 1,000 could be reduced, but we know that that's going to be a starting fraction for that rational number. Now, the number 5, if we work ourselves from the outside to the inside, is also a rational number. It's also an integer. It's also a whole number. It's also a natural number. So it would have many classifications, as again, it's a positive counting number, which makes it natural. That also includes the whole numbers. Integers are the positives and the negatives, and a rational number can be written as a fraction. Which makes me realize that we could have also said that -6 is a rational number. The square root of -4. Now remember, square root means two numbers that multiply to be that number, and we have an interesting result here that the square root of -4 has no value. This is actually another classification that we did not talk about today. We're going to be talking about it about halfway through the year. We call this an imaginary number. That's because there is no square root of -4, again, because there are not two numbers that multiply to be -4. Let's continue and talk about some different ways that we can represent sets of numbers. There's different notations when we're talking about groups of numbers. One of those is called roster notation. Roster notation is when we have a list of elements, which is really just a fancy way to say a list of numbers, but they're written in this notation when they're separated by commas and surrounded by braces or brackets. Sounds a little fancy, but it's just kind of that basic idea where if I want to list some numbers, I need to put them in a set, I need to put them in braces, and for example, if I wanted to list the first 4 natural numbers, I could write 1, 2, 3, 4, separated by commas and surrounded by braces, and I have roster notation. What if I wanted to list numbers like -6, -4, -2, 0, 2, 4, 6? Well, I can by putting commas between them and braces, but what numbers did I just list here? What numbers did I just list? That's right, they're even numbers, and they're also integers. Remember, integers can be the positive and the negatives. So I've listed the even numbers, the even integers that are between -6 and +6. But I listed them using roster notation. Set builder notation. It's just a little bit of a mathematical shorthand for being able to state precisely some numbers. This is an example of set builder notation, and I imagine you're wondering, what is this? Well, it's a vertical line that stands for the phrase such that. It's the phrase such that. And so if I was going to read this to someone, I would say I have the set of all x. That just means I have a set of numbers such that the numbers are less than 2. So we have the set of all numbers such that the numbers are less than 2. Now, that's a fancy way just to say all the numbers that are less than 2. And often when we have something in set builder notation, we choose to graph those numbers to be able to visually represent the same result. So we have a number line. We're going to mark the number 2, and I'm going to shade the numbers that are less than the number 2. and I hope you would be shading to the left. Of course, I'm not able to equal the number 2 simply because I have a less than sign without an equal sign. So you may recall that we use an open circle to represent not equaling the number 2. Could I use set builder notation to describe the numbers that are in this shaded region? It looks like I have numbers that are between -3 and 5, but we want to be precise and say that we have the set of all numbers. And that precision is accomplished by using these braces, the letter X, and our such that line. And I would read this the set of all X such that, and now I will proceed to talk about the numbers that are between, that is, that are greater than -3, but less than or equal to the number 5. And you can see that I accomplished that by saying -3 is less than X is less than or equal to 5. And again, this simply means that we're talking about all the numbers that are between -3 and 5, not just the integers, not just the whole numbers, but every number. See if you can verbalize with a partner the following phrases and see if you can, the following phrase, and in practice 3, can use set builder notation to describe numbers greater than 10. Now, perhaps you're wondering, what is this strange symbol that looks like kind of like a backwards E? Well, that is the element symbol. That's the element symbol. And really, when you read that, you say the same thing. You say that X is an element of the natural numbers. Now, what does it mean that X is an element of the natural numbers? It's just a fancy way to say that X has to be a natural number. And then we continue to read that it's a natural number that's between 3 and 9. So if you were going to verbalize that with a partner, you would say X is a natural number that's between 3 and 9. Now you could also list those numbers, and when you're listing natural numbers, remember those are just those counting numbers. So I don't have to worry about any decimals. But I could actually list all the numbers that are in that set. It would be even extra special if I put little braces around it, because that's how we describe a set of numbers using roster notation. Now, if I want to use set builder notation, I'm going to prepare myself to say X, the set of all X, such that. The set of all X, meaning the set of all numbers that are going to be greater than 10. And remember, this would be more than just 10, 11, 12, 13. This would be every number, including decimals, that are greater than 10. One more notation, it's interval notation. Interval notation tends to be one of our more common notations because, quite honestly, it only requires the endpoints. Really, it's easy to do. You're only going to need the endpoints, and then understanding that sometimes we use bracket or brackets, and sometimes we use parenthesis or parentheses, depending on if we're going to include the endpoint or not include the endpoint. Now, you've used and you've seen this notation, so let's just remind ourselves of how to do this endpoint method for a few intervals. How about numbers that are between 2 and 6? 2 is clearly the endpoint. 6 is clearly the endpoint. Because we have an equal to sign, we're going to include the number 2 using a bracket. We'll denote that with a bracket. But since we're just plain less than 6, we're going to use a parenthesis. And so when I see the number 2, comma 6, with a bracket and a parenthesis, I know we're talking about all the numbers that are such that x is greater than 2, but less than 6. How about if I see this 8 is less than x, or as I like to read it, x is greater than 8. I do like to always start with x. I would read this as a greater than sign 8. Now, 8 is definitely our endpoint, but if I'm greater than 8, if I go up from 8, then I'm going to be going up to infinity. And so because it's not equal to 8, and I can never equal infinity, I'll use the notation 8 comma infinity to describe all those numbers greater than 8. And lastly, when I see this x is less than 15, we know that 15 is definitely an endpoint, but if I'm going to be less than 15, then I'm going to go down, or you might say I'm going to start at negative infinity. You can never reach negative infinity, so we'll use a parenthesis, and since we're not equal to 15, we're going to also use another parenthesis there. Thank you, guys.
There you go.
See if you can describe each of these sets of numbers using interval notation. What I hope you see here are endpoints of -3 and 5. Because we have this open circle at -3, we're not going to be able to equal -3. We'll use a parenthesis. But the closed circle is equal to 5, so we'll use a bracket. Clean and simple, we have parenthesis -3, comma 5, bracket. There's a slight typo in this last practice. This really should be the word or, because we cannot be both of these at the same time. But if we're going to be between -2 and 2, we can use those endpoints both with parentheses, since it doesn't talk about being equal. And if we're going to be greater than 5, that's definitely our endpoint, but it goes up forever to infinity. How do I attach these two intervals? The union symbol. The union symbol is really just the same as the word or, meaning I cannot be both of these at the same time, but I'm going to have one union the other, one or the other. Now, as your homework tonight, by the way, we'll not do this book homework, but as your homework tonight, I want you to fill in this chart, which gives you an opportunity to kind of go in between each of these notations, depending on what you're given. Let's make sure you understand how to start. If you look at this first one, we see again some, perhaps some new notation. We see the element symbol and then a strange capital R. That just stands for real numbers. Real numbers are all the numbers that exist that are not imaginary. You might remember at the beginning of the lesson, we saw an imaginary number, but real numbers are all these numbers that actually exist, whether they're rational, irrational, or anything in between. So basically, numbers. Now, if I want to describe numbers that are less than 3, 3 is my endpoint, but if I'm going to be less than 3, I'm actually going down to negative infinity. Make sure that when you write interval notation that you always start with the smaller number, comma, the bigger number. So that's why I keep putting negative infinity first, and then followed by, in this case, the number 3. 5, greater than or equal to 5, greater than or equal to 5 is going to require a bracket. and then, of course, up to infinity. Once again, I wrote the smaller number first, followed by the bigger number. Union symbol to attach those. Of course, if I was going to make a graph out of this, I would be able to incorporate the same endpoints, 3 and 5, making sure that because I'm less than 3, I shade to the left, but because I'm greater than 5, I shade to the right. Notice also the use of the open circle versus the closed circle. So we want you to fill in each of these, again, depending on what you've been given, and we'll call that your homework for tonight.